Alright, so at this point you guys know everything that you need to know to be able to code up the microarchitecture for a RISC-V CPU, and that's what we're going to do for the remainder of this workshop. So depicted here is a microarchitecture for a RISC-V implementation. RISC-V, as you know, is the instruction set architecture, not the microarchitecture that's implementing the execution of that instruction set. So that's what we're talking about now, and I've depicted a very simple CPU microarchitecture that can implement RISC-V. This microarchitecture is what you'll see in any introduction to CPU architecture textbook. So I'm going to walk through the elements here kind of left to right. So first of all, we need a program counter. The program counter is our pointer into the instruction memory, into the instruction that we're going to execute next. So that PC is sent to the instruction memory as the index into the memory. The data that comes back from the instruction memory is the instruction itself, and we first need to interpret that instruction. What is this? And that's what the decode logic does. So it's going to pick apart the fields of the instruction, the source registers, the destination register. Some instructions, like a branch instruction, are going to have an immediate value, so a value encoded in the instruction itself, and the branch has an offset value as an immediate field, the offset to apply to the PC. All right, so a branch is going to take us from one instruction and then based on this relative offset to a target instruction. So this adder up here is computing the next PC for a branch. So the next PC for a branch is the incremented PC value with the offset from the instruction applied. So that's what this adder does, and then that becomes our new branch, our new PC for the branch. Most instructions are arithmetic instructions or other instructions that are operating on source registers. So we do a register file read of those two source registers. So far we've looked at arrays or memories that access one value at a time. In the case of a CPU microarchitecture, we need to access at least two source registers at a time. And so this would be what would be referred to as a two-port register file, a two-read port register file. So we get the two register values out of the register file and operate on them. And the thing that operates on them is this ALU, arithmetic logic unit. So this is performing the arithmetic. If you have an add instruction, it's performing an add, and so on. And this ALU, you've essentially coded already as the calculator example, right? So we had a calculator that had a memory. That memory is analogous to the register file. And the computation that you're performing in the calculator is the ALU. The result of the operation then gets written back to memory. So our register file also has a write port, so we can write the result back into the register file. I've depicted register file reads separate from register file writes, so we can sort of follow the instruction along through the pipeline. But the register file itself is one thing. It performs reads and it performs writes. So that's the main pipeline. In addition to that, we have memory. So you have load and store instructions. So a store instruction will go through the pipeline. It'll have a store address. And that store address is provided relative to a register. So it'll have a source register providing a base address, and then an offset provided as an immediate field in the store instruction. Those two get added together to provide the store address. Same thing for a load instruction that's going to load from memory. The store then is going to write to memory a value from the register file. I haven't actually drawn that connection. And a load is going to access the memory, and load data is going to come back and write into the register file. So I haven't really drawn here how this CPU microarchitecture would be pipelined. We're not going to worry about the pipelining just yet. we're going to jump right in and go ahead and code all these elements, assuming that we can access all of this in a single cycle. So I do have a cycle boundary after the PC, right? So each successive cycle we're going to fetch a new instruction, and there's that feedback from the next PC computation back into the PC value. Similar for a branch, computing the branch target. The instruction memory, we're going to send the address to the instruction memory in one cycle, and then in the next cycle we'll get the result back, just as we've done so far with our array, with our calculator example. For loads, we're not actually going to worry about loads just yet. This diagram is kind of magically assuming that the load result comes back immediately without any delay. Obviously, in a real CPU implementation, the memory is very large. It's likely to take many cycles to get a result back from memory. We're not going to worry about that for this workshop.